Good evening, everybody.
Evening, Steve.
Welcome to our weekly webinar. Peter Ree, founder member of the Cleethorpes District Astronomical Society, which has celebrated its 50th anniversary in 2019. He started school in the same year that the first artificial satellite was launched, Sputnik 1, in October 1957. He has followed with great interest the exploration of space ever since, and in April 1972, age 20, he was at the Kennedy Space Center in Florida to see the launch of Apollo 15, the second to last Apollo moon landing mission. Now retired, he spends a lot of his time writing and giving lectures across the country to various astronomical societies. Since 2016, has been a contributing author to the annual Yearbook of Astronomy, first published by Patrick Moore in 1962. In December 2019, Peter was elected a Fellow of the Royal Astronomical Society for his contributions to astronomy over the last 50 years. So please welcome our speaker tonight, Peter Ree, in a good Mexborough and Swinton Astronomical Society way. Thank you.
You should be seeing that. I've got lots of faces on the right hand side of the screen, so I'm just going to minimize those so I can't see you, so I can see the whole of the screen. Right, well, good evening, everyone. It's been a while since I spoke to the Mexborough and Swinton Astronomical Society. In fact, it's been 2 years and 2 days because I last spoke to you at your 2018 AstroCon. When I gave a talk on Mars, a guided tour of the Tharsis region. I love the planet Mars. I think it's absolutely fascinating. But we're talking on something a little bit different this evening, the Space Shuttle history in 3 parts. And it's quite staggering to think that it's 9 years, just over 9 years, since a shuttle flew from the Kennedy Space Center. And in this trilogy of talks, I want to discuss with you this quite remarkable flying machine. And whilst it's an amazing piece of engineering, the shuttle system certainly had its flaws and also its many critics. Sadly, 14 astronauts were to lose their lives in 2 missions, and we'll talk about those in part 2. So I guess you could say that the shuttle history is one of triumph and tragedy. The Space Transportation System, to give it its correct name, was intended, when it was designed in the 70s, intended to replace all expendable launch vehicles, those that are used just once and are thrown away and their stages end up in the Atlantic Ocean. And we were confidently expecting to see launches, every 2 weeks or more, 25 odd per year, at greatly reduced launch costs. Well, I'm sad to say it was none of these at all. And my mouse tonight is a bit active. The Space Shuttle program was active between those years you can see on your screen, 81 to 2011. That's 30 years in total. An amazing history in which they launched a total of 135 missions, not the 500 odd we were promised. And a total of 355 people flew on the shuttle. Now, if you were to add up the crew totals for those 135 missions, you'll come to a lot more than 355 people, because some people flew more than once, some up to 4 times. But 355 is the number of individual people that flew on the Space Shuttle. And as part 1 is called Origins and Concepts, I think we need to just take you back a few years, well, a few decades really, to see where the shuttle design started. And we go back to the late 1930s, just pre-Second World War. and famous aerospace engineer Eugene Sanger designed what he called the Silver Vogel, or Silver Bird in English. It was a suborbital bomber designed to attack America, and it was to be launched across the Atlantic on a suborbital trajectory and fly across the Pacific Ocean as well and back into Europe. This vehicle could be classed as one of the early predecessors of what was then called space planes, which would later be called space shuttles in the 70s. And it used a technique that was at the forefront of thinking in space planes for at least a couple of decades, and that was to launch them horizontally up to a ski jump at the end of the track, where they would be launched into the air. You can see the silver looking booster rocket at the back and the white coloured silver Vogel right at the front with the German markings. And this was sped along a track quite a few miles long until it hit a ski jump and then went into the suborbital trajectory. And that idea of launching horizontally or up a ski jump was active for quite some time. And this is a still from a film that came out in 1951, When Worlds Collide. A rogue star was approaching the solar system, and they needed to get people off it and onto another planet that was surrounding this rogue star. And you can see in the inset in the top right a slightly better image of that rocket, which has great similarities to the German V2 rocket that bombed London during the Blitz. And that was set off along this track, downward at first, and up the side of a mountain, where it turned vertically and went off into space. Now, come on, you guys, you must admit you remember the 1962-63 puppet series Fireball XL5. Pictures from the black and white TV series at the top and modern computer graphics at the bottom. But what is interesting about Fireball XL5 was that it used the concept that was quite popular at the time of not launching vertically but launching horizontally, and this features quite a lot in our story of the Space Shuttle. And it was boosted along a 2-mile track, and yes, we've got at the end the famous ski jump which took it into orbit. You can, if you wish, admit you actually watched Fireball XL5. But launching horizontally or launching vertically, this was something that had to be addressed. All passenger aircraft and most fighter aircraft will take off horizontally so that they can gain lift over the wings, which lifts them into the air. There is, of course, an exception to this, and if I may express a private opinion, that what we're seeing here is one of the greatest aircraft ever developed in this country, if not the world, the Harrier vertical takeoff fighter. But yes, it can take off vertical, but its payload is limited. Science comes into play here because we've got the weight of the aircraft and gravity is pulling it down to the ground. So the power of the turbofan engine has to be greater than the weight of the aircraft in order to lift it off the ground vertically. And this does tend to limit the payload. So the thrust has to be greater than the weight, or to put it in correct parlance, the thrust to weight ratio must be greater than 1. If it is, it can take off vertically. If it isn't, it can't. But this limits payload. So how do we increase payload? Well, of course, that is take off horizontally and gain aerodynamic lift, which the Harrier did on board aircraft carriers, Hermes, Invincible, Illustrious, Ark Royal, and all of that. And again, it used this ski jump. So once you've accelerated down the ship, you're effectively thrown into the air, a concept that comes from these early space planes. So in the late 50s and early 60s, they're seriously starting to look at space planes. They were still called space planes in the late 50s and early 60s. And there was this question that had to be asked. Do we take off horizontally with the shuttle on our back, as you can see in the upper two pictures, or do we take off vertically with the shuttle on its back, as we can see in the bottom left? And in both of these scenarios, the booster that is carrying the space plane on its back is also capable of returning back to the runway. In other words, these systems envisaged here are totally reusable, and this is what was the key to keeping the launch costs down. However, developing these systems proved extremely difficult in the development phase because they were very, very expensive, and Congress simply wouldn't give NASA the money to build a totally reusable system. In hindsight, if the program like these had lasted the same as the shuttle program did, that was 30 years, then almost certainly the through life cost would have been cheaper. But they balked at the initial cost of developing a totally reusable system, so something else, a compromise, had to be developed. But before that, we had to do a lot of aero research on high-speed flight. In coming back from orbit, the space shuttle would re-enter the Earth's atmosphere at Mach 25, 25 times the speed of sound, 17,000 miles an hour. No aircraft had ever flown that fast before, and they needed to expand the flight envelope, as it's called. That is height and speed through the air. And the X-15 research aircraft, which started flying in 58 and went through to 59 and went through to 68, flew a total of 199 times. Why it never did 200 is beyond me. But those 199 test flights, and all of them were test flights, was conducted by 3 aircraft. And the maximum speed achieved through the air was 6.7 times the speed of sound, equating to slightly over 4,500 miles per hour. And it reached an altitude of 67 miles. And it was lifted into the air under the starboard or right wing of a Boeing B-52 bomber. And you can see it just being released there. So the X-15 didn't take off from a runway. It was carried into the air and then released because it had a rocket engine in the back which accelerated it to the speeds we've discussed already. And one of the X-15 pilots was this gentleman here, and I'm sure you'll recognize him as the first man on the moon, Neil Armstrong. What they also had to develop was what was the shape of the wing. Because with you entering the Earth's atmosphere at very high speed, conventional fighter aircraft wing or commercial aircraft wings would simply be ripped off. So these are 3 X-series or experimental series of lifting bodies, as they were called. They didn't really have wings. The body just blended into a vertical surface, and they were trying to refine the shape of the nose and the body and any vertical surfaces. And in the middle you can see what would become a rather famous lifting body, the Northrop M2F2. It's famous because of a crash which occurred while being piloted by Bruce Peterson. Not his fault, it was a control issue, and it caused the M2F2 to crash and tumble along the runway. If you recall a TV series called The $6 Million Man, the introduction to that, the title run-up, shows the M2F2 crashing and tumbling with Bruce Peterson at the controls. And that gave the inspiration for rebuilding the pilot, as it were, as the $6 million man, and that is a publicity poster. Unfortunately, the publicity department didn't realise that the plane or the lifting body that Peterson was flying was the M2F2, because they've actually illustrated the HL10, which you can see on the right. And the research aircraft that probably came closest to defining the shape of the shuttle wing was the Martin Marietta X-24B, here seen over Edwards Air Force Base in California, and that is the dry lake bed, and we will encounter that again a little bit later as the shuttle was tested in the Earth's atmosphere and came into land on that very, very lake bed that the X-24B is going to land on. There was also a program which lasted from 57 to 1963, the X-20. It never actually made it into space. It was called the Dyna-Soar, a contraction of dynamic soaring. In this country, we tend to call it gliding. In America, they tend to call it soaring, and this would glide back through the atmosphere and land on a conventional runway unpowered, which is exactly what the shuttle did. But this never made it beyond the drawing board stage. By the early 1970s, the compromise shape of the space shuttle started to appear. And you can see concepts there from 1972 on the left right through to 1974. The one on the right is fairly close to the modern or current design of the space shuttle, which had this double delta wing. And you can see the arrow is pointing to this delta wing or triangular shaped wing, which has got two specific angles, quite a shallow angle near the nose, and then it tapers out towards the outer edges of the wing. This shape was all developed from those lifting bodies. So this is an up-to-date picture of the first shuttle orbiter to go into space, not the first one built, but it was the second built, but the first to go into orbit, called Columbia. And instead of being launched on the back of a reusable aircraft, it was launched on the back of an external fuel tank, which you can see here painted in orange, which was the colour after the third flight and right through to the end. The first two missions were launched with a white tank. So we have an external tank to which is mounted two solid rocket boosters, by solid fuel boosters to be more precise, rather than liquid fuel. I'll explain that very, very shortly. And then onto the back of the external tank was the shuttle orbiter, and you can see a view from the front, back and one of the sides, as well as the top and the bottom. So the propulsion system was twofold. The shuttle orbiter had three very powerful liquid fuel engines deriving the fuel from that big external orange tank, and the rest of the fuel, the thrust at liftoff, in fact 80% of the liftoff thrust came from those two solid fuel boosters. The liquid engines on the orbiter were canted out at a slight angle towards the vertical tail surface. And there was a very good reason for this, because with the orbiter being mounted on the side of the external tank, if those rocket engines in the back of the orbiter were pointing straight down, you would end up with asymmetric thrust, that is offset thrust, and the whole tank would, the whole system would just flip over at launch as soon as the engines were ignited. So common practice is to cant out the engines so that they're what they call the thrust vector, the line that the thrust is lined up on, is on the center of mass of the whole launch system, the external tank boosters and orbiter, and that's why they're canted out slightly, so the thrust goes through the center of mass and therefore it can lift off vertically. Those are the two external, the two strap-on boosters to the external tank, and what made the shuttle system quite unique when we start talking about part 2 and 3 is the enormous, quite cavernous cargo bay, which was 60 feet long and 15 feet wide, capable of carrying about 25 tons, far in excess of any conventional rocket available at the time. So I've mentioned liquid fuel rockets and solid fuel rockets, so I think it's just necessary to explain the difference. So with liquid fuel rockets, and in very simple diagrammatic terms, you will have a fuel tank, and because you're going up into space and into a vacuum, you need to carry your oxidizer with you. So it will have a fuel tank and an oxidizer tank. There will be two very, very powerful turbo pumps which will pick up the fuel from the two tanks and push it at high pressure into a combustion chamber where the fuel and the oxidizer are mixed and ignited. Effectively, they explode, but the combustion chamber contains the explosion and the hot exhaust gases fly out the back. What you want is for those exhaust gases to fly out the rocket nozzle as fast as possible. Remember that famous equation or saying by Isaac Newton that action and reaction are equal but opposite. So the faster the exhaust gases go out to the right, the faster the rocket can go to the left. And rocket engines are far more efficient in space, in a vacuum, than they are within the atmosphere. And that's just a photograph of a liquid fuel rocket burning with a fairly transparent flame. But a solid fuel rocket is quite different. The fuel starts off as a liquid but is then cured. If you were to get some of this solid fuel in your hand, it's very similar to a pencil rubber. It's actually quite bendy, and that's the kind of the consistency of this solid fuel. It's rubbery, really. And I know we've got November the 5th coming up, and no doubt people will be letting off firework rockets. But if you were to ignite a firework rocket, that is, light the blue touch paper and run like hell, the firework rocket will burn from the bottom through to the top and are not particularly efficient. But with modern solid fuel boosters, they don't burn from the bottom to the top. There is a hole running right down the center, and there's an end view of it, so you can see the solid fuel, but there's a hole punched straight down the middle. So once the igniter, which is at the top, ignites all that fuel, and there she goes. And if you look at the bottom bit, the circular diagram, you will see that the solid fuel booster is burning from that hole outwards rather than from the bottom to the top. And this is a far more efficient way of burning that fuel. And there's a photograph of one of the shuttle boosters under test, and they deliver, the pair of them, about 80% of the liftoff thrust. And solid fuel boosters are quite common. They've been used for many, many years. They're generally considered to be safe and reliable. The liquid fuel engines have one big advantage. They can be throttled up and down, and they can also be shut off if necessary. With solid rocket boosters, once they are ignited, you cannot shut them off. They have to burn out before they can be safely separated. It was a weakness of the shuttle system, but the whole design was a compromise on what the engineers wanted rather than what Congress was prepared to pay for. Now, the boosters for the shuttle were the biggest ever built. So big, in fact, that they had to be built in segments. The manufacturer of these boosters, Morton Thiokol, were based over in Utah, which is quite some distance from the East Coast and the Kennedy Space Center. So the individual segments were pulled right across country, individually, on rail tracks, all the way over to the Kennedy Space Center. And you've got enough there for just one of the pair of boosters. And once they're offloaded at the Kennedy Space Center, they're taken into that big cube-shaped vertical assembly building. If you've been to Florida and you've been to the Kennedy Space Center, that building just dominates the skyline for miles around, and that's where the boosters are assembled. Now, this is two segments coming together. Where they are connected is called a field joint, and in order to maintain a little bit of flexibility in these joints, neoprene rubber O-rings, a pair of them in the early days, up to the Challenger accident, a pair of these rubber O-rings sealed this field joint. We will return to that image and the field joint and the neoprene rings in part 2, when we talk about the loss of the two orbiters, Challenger and Columbia. This is the top end of the boosters. They are recoverable after a launch. Inside those cones are parachutes, which allow these boosters to descend down into the ocean, where they are recovered, brought back to the Kennedy Space Center, dismantled, and sent back to Utah for washing and refilling with fuel, ready for a later launch. This mobile platform is from the Apollo days, where the big Saturn V rocket was assembled in the vehicle assembly building, part of which you can see on the left side of the screen, and then it was wheeled out with a monstrous device, big tracked vehicle wheeled out to the launch pad. And that system of wheeling the Saturn V out to the launch pad was adopted for the Space Shuttle. But the first element to go on the mobile launcher platform were the two boosters, followed by the external tank, and finally the shuttle orbiter itself. Just to give scale to the boosters, I'm showing you this picture, which shows 3 people at the exhaust nozzle, and that kind of gives you some idea of scale. If you want the facts, then each of these solid fuel boosters generates 1,250 tons of thrust at liftoff, or the pair of them 2,500 tons of thrust, which enables the whole system to lift off vertically. You just need raw power to lift off vertically. We've already mentioned the shuttle main engines, the liquid fuel main engines, of which there is one under test. It's fueled by liquid hydrogen and uses liquid oxygen as the oxidizer. And therefore, this is the most efficient combination of fuel and oxidizer, because hydrogen is the lightest element, and the lighter it is, the more you can have on your external tank. And you'll notice it's burning with a, well, almost transparent flame. It's non-polluting. Effectively, that's just high temperature steam coming out the base of that rocket engine. But there are some staggering facts about that Space Shuttle main engine. It generates at sea level 186 tons, just one of them. And that exhaust you see coming out there is round about 3,000 degrees Celsius, incredibly hot. And the fuel consumption, wait for it, is 350 gallons per second, not per minute, not per mile, per second, 350 gallons. Just take a look at that small thumbnail there. It's actually of a 35-gallon water butt. So if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 35-gallon water butts, then that is how much fuel is passing through that engine every second. And there are 3 engines in the base of the orbiter, so therefore 30, I've lost my train of thought, 350, oh, I can't work it out, sorry. This is starting to happen more and more regular now. I put it down to my age, really. Just lost my train of thought. Never mind, that's with little dignity. Move on to this last slide. So these are the 3 Space Shuttle main engines. We've already seen that they burn with a transparent flame. This is shortly after liftoff. And again, just to show scale, I wanted to show this particular picture of a couple of engineers installing engines in the back end of the Space Shuttle Orbiter. It just gives some idea of the size of them. So they are in like a triangle formation. Notice on either side of the upper engine, there's a little red casing. This is covering up some orbital maneuvering engines, which are needed just to finally place the vehicle into orbit, and are also fired to slow the vehicle down so it can re-enter the Earth's atmosphere. More of that's in part 2. So this is the mighty external tank, and it is just a tank. It's essentially hollow. It's about 30 tons when it's empty and over 700 tons when it's full. The oxygen, or liquid oxygen, covers the upper third of the external tank, and the liquid hydrogen covers the lower 2/3 of the tank. And they are built in Louisiana, which is not too far away from Florida. You have to put it on a barge and take it across the Gulf of Mexico, round the tip of Florida where Miami is, and then up the east coast. And you can see it here arriving at Florida. On the horizon, right in the middle, you can see that big assembly building. And the barge carries just a single external tank, and you can see it just being wheeled out there. And again, the obligatory people in the picture, just to give scale to the size of that external tank. Here we can see the shuttle orbiters in a fairly early stage of building. And in this black and white picture, you can see the first orbiter or space shuttle to be completed, which was Enterprise, never destined to go into space. This would be used for tests within the atmosphere. And to the right of the picture, you can see the Challenger in a quite early stage of construction. A picture looking underneath the completed orbiter. The left-hand image shows just one of the main undercarriage. There's a pair of those. And on the right-hand side, you can see the nose landing gear. And you can see on the nose and underneath the vehicle some black tiles, similar to tiles you'd have in your kitchen or bathroom. And there were thousands of these black tiles, troublesome in the early days, but throughout the 30-year life of the shuttle, they proved extremely reliable at rejecting the enormous heat of re-entry through the Earth's atmosphere, where the nose and the wing leading edges would get up to about 1500 degrees Celsius. And also in the nose, you can see four holes. These are the exhaust to thrusters, which are used to pitch, roll and yaw the orbiter in orbit, and also translate it forward or back, or up or down. And there you can see some of these tiles being fitted in the top right hand corner. They are all individual because of the shape, or the aerodynamic shape of the orbiter. There is not one single tile that is the same as another. They are all individually made, and in the bottom left you can see a reference number there. So if a tile is damaged at all during a mission and it needs to be replaced, then they have to look at the number and have another tile made to exactly that number and size. And you can, another picture of them on the nose in the upper left, and in the bottom right you can see a test sample of one of these tiles, which is made of silica mostly, and it's glowing white hot as it comes out of a baking oven, yet there's a person there grabbing it by the corners or the edges, and they can pick them up. These tiles are so efficient at rejecting heat, you can pick them up with your fingers whilst it's still glowing white hot in the center, and it doesn't burn you at all. That's how efficient they were. On the nose and wing leading edges, you had a slightly different substance. This was referred to as carbon. And if anybody is a Formula One fan, I am one, then this shows one of the brake ducts of a Ferrari F1 racing car, which also uses this carbon material, because you need that for the brake discs to withstand the enormous heat on Formula One racing cars as they come up to a corner and slow down from a 200 and something miles an hour to 50 or 60 miles an hour or so in just a few seconds. Those brakes glow white hot. You may well have seen it. Same material that's used on the wing leading edges of the orbiters. On upper surfaces, which don't get so hot as the nose, wing leading edges and the belly of the orbiter, the upper edges are covered in special heat rejecting blankets, which you can see here in white. So upper surfaces on the shuttle were always white. They can still withstand temperatures of many hundreds of degrees, but the high temperature areas are black, or the wing leading edges, this silver carbon. This is the back end where the engines are and the rudder, that vertical tail surface to control yaw as it's coming in through the atmosphere. And you can see these blankets on one of the side pods, which houses fuel, which supplies the thrusters and those maneuvering engines at the base of the at the back of the pod that I've already mentioned to you, which are used to slow the orbiter down to sufficient to let it re-enter the Earth's atmosphere. And you can see 4 thrusters there. There are also some that you can't see, but they're on the upper part of the pod, that there's some facing up and there's some facing down. That device there is used to connect umbilical connections from the launch pad, so that the launch control people can communicate with the orbiter through those connections, which are disconnected at the instant of liftoff. The orbiter crew compartment is on 3 levels. The upper deck is the flight deck, where the commander and pilot sit and 2 other crew members immediately behind them. There is a mid deck where up to 3 more astronauts can sit for a crew complement of 7. There are sleeping compartments there, and a great luxury from the Apollo days, there's actually a toilet that you can use. Don't ask what the Apollo astronauts had to do, but on the shuttle mission there was a toilet you can use, and that was if you'll pardon the expression, a great relief. There is a lower deck as well, which houses a lot of electronics, which is accessible from the mid deck. So the mid deck is where they eat, sleep and do everything else you need to do as well. And this is the upper deck looking forward. So this is where the commander sits on the left, pilot on the right, and there's a photograph of the cockpit in the very early days of the first half of the missions. This is technology that was designed in the late 1970s, early 1960s, And you can see the computer screens there are these green phosphor screens that we used to have in the very early days of computer screens. We don't have those now, but we did in the early 1980s. And just for the record, that's what they look like after major refits in the 90s and the early 2000s. Much more accurate and precise screens, which giving the crew a lot more information. And this is in the it's in the upper deck. And this is, look, the window you can see just above that hand controller is looking out into the payload bay, because when you're deploying payloads, you need to look out through two aft facing windows, and you can see controls there and a joystick, and the shuttle orbiter can be positioned not from the commander and pilot seat at the front, but from this aft facing cruise station, and they can control the pitch, roll and yaw and the translation up, down and lengthways of the orbiter from this backward looking station, so they can look out at the payload that you're wanting to deploy. And this is in the mid deck looking forward, and you can see stowage boxes there for food and all sorts of things. You can see a couple of seats that crew would sit on for launch, but once they've achieved orbit, these seats are stowed away so that they're not getting in the way and there's more room to move about. And I've already mentioned Enterprise, the first orbiter to be completed, but it had no thrusters on board. It had no engines at the back other than dummies for mass simulation, and this was destined not to go into orbit but to be tested within the atmosphere. And recall, of course, that something has to lift this into the atmosphere so that they can drop it, and I will explain what that was in a moment. But this is a photograph of the two crews. Fullerton and Hayes were one, Engel and Truly were another. So there was two separate crews for a series of approach and landing tests. And NASA bought a couple of ex-American Airlines Boeing 747s and modified them. They modified the tail and they put some attachment points on the top of the Boeing 747s. And the crews who were going to fly these were told that they would be transporting the Enterprise into the air. And I think we might just have the wrong Enterprise there. That was the Enterprise that they had to carry into the air. And you'll notice that the nose is slightly high on the orbiter. This is so that it gets a lot of lift as it's going up. So this is one of the first test flights, and the jumbo jet takes it off and took it to about 30,000 feet and over Edwards Air Force Base, and it was to release Enterprise whilst it was travelling in the wrong direction, as it were. It was flying away from Edwards Air Force Base, so what it had to do was demonstrate that it could do a 90-degree turn followed by another 90-degree turn. So now it's flying in the opposite direction and in the general direction of the runway. At the precise moment, explosive bolts would fire, severing the connection between Enterprise and the jumbo jet. The orbiter would climb slightly and turn to the right, and the jumbo jet would immediately go into a shallow dive and turn to the left. So you were getting vertical separation as well as left-right separation. It was therefore necessary to do the first of the the left-hand turns, the 90-degree, to start to line it up with the runway. And there it is, going through the first, and then it did it again, so it's gone 180 degrees. Notice there is an aerodynamic cone right at the back of the orbiter. This was to enable the jumbo jet to get it up to about 30,000 feet without that cone and having dummy engines at the back, there was too much drag, and the jumbo jet could only get it up to about 25,000 feet. So we're turning towards the runway. Here we are, and that's that lake bed that I showed you with the X-24B. It's a very, very similar photograph. So it's turning to line up not with the concrete runway at Edwards, but the lake bed, which has a runway about 12 miles long. The concrete runways built for the shuttle were going to be 3 miles long, but for the first test flights, they landed on the lake bed. And that's that image again, showing the lake beds on both pictures. So this is Enterprise coming in on the left just before wheels touchdown. The date was the 12th of August 1977. I remember being glued to the television and watching this. And on the right we have touchdown, because you can see the dusty bits of the dry lake bed coming off the wheels. And once they'd done a few of those, they then did the tail cone off flights, now representative of what it would be like coming back from orbit. But of course, as previously mentioned, these were dropped from a lower altitude because of the drag on the 747. And that date, 12th of October 77, was the first landing with the tail cone off. So once we had these flights, the approach and landing tests in 1977, the whole thing was cleared for flight through the atmosphere. What had to be demonstrated, and there was only one way to demonstrate it, that coming back from space, was to actually launch one into orbit and into an environment and a flight envelope that had never been tested before. And the launches would be taken place at the Kennedy Space Center. They were considering a shuttle launch pad at the Vandenberg Air Force Base on the West Coast in California, but that was never completed, and no launches ever took place from Vandenberg. All launches took place from the Kennedy Space Center. That triangular bit of land is called Cape Canaveral, which is an Air Force station and where lots of the expendable rockets are launched from. And that arrow is pointing to Merritt Island, which is where the Kennedy Space Center is built. Cape Canaveral is a military establishment. Kennedy Space Center is a civilian establishment. Lot of confusion in the news, the newspapers and the TV news, on the difference between Kennedy Space Center and Cape Canaveral, because I heard on more than one occasion that the Space Shuttle whatever landed today safely at Cape Canaveral. Well, I hope it never did, because there wasn't a runway there capable of taking it. They all took off from, and some of them landed back at the Kennedy Space Center. This is Port Canaveral, which is the entry point for those external tanks on the barge. Comes into Port Canaveral, then it goes up that river, the Banana River. The India River is to the left of Merritt Island, and they could go up to the just short of the launch pads and go into a special turning basin, which is indicated just there. It's just outside the vehicle assembly building, that cube-shaped device. I'm sure you've seen that. And that's Launch Complex 39, which was built specifically for the Apollo moon missions. Pads A and B, pads C and D to the north were never completed. So only pads A and B were used for Apollo. Well, most of them went from pad A. Apollo 10 was the odd one out. It went from pad B. But the shuttles were launched from both. And that white streak there is the shuttle landing runway, about 3 miles long. Great picture there from the Earth. The red circle shows where the turning basin is for when the external tanks come in, and you can see the closeness of that to the big assembly building just to the left of that circle. In the distance, you can see Launch Complex 39 with pad A to the right and pad B to the left, which are the northerly pad. And these are the two pads, A at the bottom, B and the northerly pad at the top. Like all runways, whether it's at Heathrow, Manchester or Kennedy Space Centre, runways have got two ends to them. And you can come in from either end depending on the wind direction at the time. And you can come in from the northwest, and if you come in from the northwest, then your guidance system will be putting you on a heading of 150 degrees. So therefore that runway is known as runway 15. If you come in from the south, you're coming in from the southeast, and your instruments will be telling you you want to be on a heading of 330 degrees. So therefore the pilots will be told you need to land on runway 33 if you're coming in from the southeast. So that's that big building. I've had the pleasure of going in that 1972 with Apollo 16 on the pad, and Apollo 17 was being assembled within the vehicle assembly building. An astonishing sight. What a huge building. So here we are, practically at the end of the talk, and this is Columbia with its white painted tank, not the orange painted tank. Columbia on the eve of this first launch in April of 1981. And we'll take a look at that in part 2. And I will leave you for the time being with this picture of the very first crew to fly this test mission, STS-1, Space Transportation System 1. That's John Young on the left and Robert Crippen on the right. And they are awaiting their place in history with the launch of the first space shuttle. But we'll talk about that next time. In part 2, we talk about the shuttle as a satellite launcher, on which it was extremely expensive and not very successful, and also a repairman, on which it excelled and gave the Americans a unique capability that no other country had. That's in December, and in February, the Space Shuttle Story Part 3, which simply entitled Science and Assembly. And this was science missions and assembling the International Space Station. This is where the shuttle was in its element, and it was a unique capability that the Americans had. But for now, we are to be continued, so I will escape from that, stop sharing my screen, and hand you back to the chair.
Thank you, Peter. As always, your talks are fascinating, and they lead us through so much history and so many memories. Thank you for that. We're going to go on to questions now. As people are gathering their thoughts, can I remind you, put a digital hand up preferably. If you can't find a way of putting a digital hand up, wave at me. So whilst people are thinking, Peter, your slide of the pre-assembled SRBs, the ones that were loaded on the train, had yellow boxes between the sections. Was that just a safety feature, just in case they accidentally ignited?
Well, I'm not exactly sure what those yellow boxes are, I'm slightly embarrassed to say. But they're not likely to accidentally ignite. It takes a very high temperature to ignite that solid fuel. If I had a piece of solid fuel in my hand, I could actually strike a match and kind of put it underneath. And instead of blowing my head off on the roof here, it wouldn't really ignite. The match flame wouldn't be hot enough. You have the special igniter on these boosters right at the very top is two chemicals that come together and send an extremely hot flame straight down the center of the tube, that hollow tube, in order to ignite it. So transporting them across land is relatively safe, far safer than transporting nuclear material or anything like that, which do need special containers. So in answer to your question, what were those yellow boxes? I'm not exactly sure, but the chances of an accidental ignition was extremely low.
Okay, thank you. Lewis, can you mute yourself, please?
Okay, my question is, you know the Northrop M2F2?
Yep.
Do you know how it got its name?
Well, Northrop is the name of the company. M2, F2, I don't know how it actually got its designation. There was also the HL10. I know HL stood for horizontal landing. I'm not too sure about M2, F2, but the name Northrop, and on an earlier one, on that particular picture, there was one called Martin Marietta. This was the Glenn L. Martin Company, stationed in Marietta, which is a city in Georgia, a state in America. But Northrop wasn't. It was named after Jack Northrop, who built a lot of fighter aircraft for the Navy in the early days, and they did a lot of work on the shuttle program, and later teamed up with the Grumman Company in Bethpage in New York to form a company that is in existence now, known as Northrop Grumman, and they do a lot of work for building fighter aircraft for the Navy. So that's where the name Northrop comes from. But I'm not exactly sure where the M2F2 name comes from. I will look that up, and I will. I don't have your email. I don't need to know that, but I can. Do you actually have an email?
Yeah.
Right. Okay. I don't need to know it, but I can. Steve, perhaps I could relay it through you if I can find out what M2F2. M2F2. Right. If I can find out, I'll email that into Steve, and he can send it off to you. So I don't need your email.
Okay, Lewis. Thank you. Have you got a follow-up question, Lewis?
No.
No.
Fine.
Thank you for your question.
Thank you.
And I'm looking for other questions. Dave and Jan. Welcome, Dave and Jan.
Thank you.
Can we have your question, please?
You can. Peter, that was absolutely brilliant. I thoroughly enjoyed it.
Thank you.
My question is, you mentioned a few times about those boosters being orange and white. Is there a reason why the colour went from orange to white, or?
Yeah, from white to orange. Yes, the first two, STS1 and 2, were painted white all over, so that it matched the colour of the orbiter as viewed from the top and the boosters as well. However, that white paint added up to a quite amount of weight, which was totally unnecessary. So by STS3 onwards, they stopped painting the external tank, and therefore what you're seeing is the spray-on foam insulation, which is a natural orangey colour. And so they saved, I can't remember exactly what the weight was, but it was just over 1/2 ton of paint just to paint the external tank for cosmetic reasons. So by not painting the external tank, they saved about 1/2 ton of weight and an awful lot of cost as well. Can you imagine what 1/2 ton of paint costs? So yes, it was a cosmetic appearance that they decided to get rid of. So you're seeing the base colour or the natural colour of the insulation on the external tank, because those tanks had to be insulated because they're holding very, very cold liquids. I mean, liquid oxygen, liquid hydrogen are -200 and something, very, very cold indeed. And on summer days in Florida, it can get to 80 or 90 degrees atmospheric temperature. So you need to insulate the fuel so it doesn't evaporate off, and that's the reason they got rid of the paint.
Thank you.
Okay, we're down to 2 questions. Anybody got Phil Muffett.
Yeah, hi Peter. Nice talk.
Hi, Phil.
Space Shuttle's a bit of soft subject for me as well, soft spot. But I downloaded a program called Orbiter. It's free on the internet. It's bug free, and I've ran it on Windows.
You've muted.
You've muted yourself,
Phil,
Peter.
you've muted.
Philip.
Oh, I'm sorry, it caught the button. Yeah, so yeah, I've downloaded Orbiter. It's a free space shuttle flight program, and you can run it on your PC with a keyboard, and it's really good experience to learn how the space shuttle flies in space. You can launch it and land it as well, but I'm trying to get to grips with space dynamics and geometry and stuff, and it's really good. And you can launch and capture satellites from the cargo bay as well with a remote manipulator. It's called Orbiter if you're interested.
Orbiter, right. Yes,
it's worth looking at.
It's a very complex system because the space shuttle launches vertically like a rocket, and then it acts like a spacecraft in orbit because it's in a vacuum, but then it comes back and lands like an aircraft. So there's these. It's a rocket, spacecraft, and aircraft all in one.
Yeah. It's interesting.
Yeah, I'd love to be able to do that. I wonder how many times I crashed it.
Well, you don't have to launch it and you don't have to land it, but you can fly it in space. That's the best way to start. Just to learn how it moves, yaws and pitches. There's different levels you can go at, but it's worth doing if you're interested.
Fantastic. I appreciate the information.
I'm looking forward to seeing the upgrade of your simulator, Phil.
I'll do it one day.
Okay. I thought I saw young Lewis with another question. Lewis, have you got another question? No?
I just wanted to ask Philip, do you have to use a keyboard, like a plug-in one? Because I tried it before on my
Yes, you do. You want to plug in an external keyboard to use Orbiter, because it's something with the key configuration, but it's good. You can do it easily.
Okay, ladies and gentlemen, I think we'll let Peter go at this stage. Can we give him a rousing Mexprin Swinton Astronomical Society? Thank you for a wonderful talk.
Thank you. Appreciate it.